in these field applications, there are a few configurations that I want to talk about. The first configuration is this ground to ground. Essentially, here we just test the pointing and tracking system and say, well, let's have nothing be moving. The drones are on the ground, and let's just see if we can actually, do QKD on the ground. And it turns out that we can, but you can see from the plot here that it's a little bit more difficult to try to keep them aligned than it is on the table. You can see sometimes there is even a drop in signal in the plot here. You'll notice the difference between the intentional drops and the drops that are actually because we're actually in a field application. And as you can see in the results here, we are able to get first of all, the QBER is well below the 11% limit that we talked about earlier. That means that we can get a secure key. And then additionally, the raw key rate of our system is 165 kilobits per second. And then the secure key rate, this is after going through error correction and private simplification, is 6.05 kilobits per second. So this is great. That means that the pointing and tracking system actually works. And we're also able to, that the pointing and tracking system works, and we're also able to demonstrate that the QKD system itself, it's able to be integrated with a mobile platform like drones in this case. Now the question is it light enough for us to actually fly with it? And the answer is yes. So the next configuration that we do is, okay, let's fly these drones and let's see if we can actually get some quantum key distribution going. And as you can see from this plot right here, you might be able to say, wow, that sucks. But it turns out that it's actually we're actually still able to get a secure key out of this system. But you can see from the plot that this is not a smooth ride. It's the pointing and tracking system is working really hard here to maintain alignment, but you can still see some patterns in this data that you see here compared to. I know it looks bad compared to the tabletop data, but it's still good data, quote unquote. And so this system, and specifically the drones, are flying in the air at an altitude of about 5 meters from the ground, and they have a separation of about 10 meters from each other. And they're flying around, and they're swaying, and we're actually able to get the key, a secure key of 7.98 kilobits per second. And this was the task that we set out to accomplish. And so mission done for us here. However, we didn't want to stop there. We know that there were other gaps in the image that I showed earlier. There are other gaps that we could fill using this kind of QKD system. And so we set out to do that exactly. And the next step that we took is we said, okay, so we know drone to drone works. Can we actually do this from a moving car to a moving drone? And so that was the next step in our experiments. And what we did is we put Bob on top of a car, as you can see an image here. And then Alice is flying next to the car. And they're both moving forward at a speed of 10 miles per hour. And in this case, because we're in a private property here, we're actually able to turn on all of the lasers and everything. All the pointing and tracking system is working, both pointing and tracking systems are working. And so we're able to actually get some information out of this system. First, the QBER, again, is well below the 11% limit that I mentioned before. And second, the data is enough so that we can actually get a secure key out of the system. In this case, we're able to get 1.52 kilobits per second. And so this is great. This is yet another configuration, another gap that we're able to fill in the QKD space. But now we wanted to go even farther. And then we said, okay, what if we try car to car now? And you might think, well, isn't like drone to drone harder? Well, in the highway, it's the unpredictability of potholes and things like that it's very difficult to keep things aligned to each other, and especially when you're in the first experiment that we did for these two for car to car. We placed Alice in one car and Bob on the other car on their windows, and then they're pointing to each other. And in the first experiment, where we do car to car at 5 miles per hour, we do it on a specifically designed track where they test roads and cars. So this track is specifically very smooth. And you can see in the data that we collected here that the data is very smooth. And then in this case, as I said before, we are able to turn the lasers on because we are on private property. However, when we try to do this on a real highway at 70 miles per hour, we're not allowed to do that. It's illegal to have lasers coming out of a car and pointing to the free space in the air like that. So because that's illegal, we're not allowed to. Essentially, the second control loop, which is the fine control loop, it wasn't on. We couldn't turn it on, and therefore the alignment was not great between Alice and Bob. And as you can see here, the secure key rate that we were able to get is 0. We weren't able to get any secure key out of the system. We're still able to get a raw key out of the system, 9.26 kilobits per second. And even though the QBER is below 11% limit that I talked about earlier, because the alignment wasn't there, we were not able to get the secure key that we wanted. And so those are all the configurations that we try, and this is kind of the summary of all of these configurations. And so just to summarize the work that we did here, we built a compact QKD system for implementation in mobile platforms. This system proved to be robust and capable of generating secure key in real-world conditions. And we implemented it in highly mobile platforms like drones and cars. And just to give it a comparison with some what were state-of-the-art experiments a few years ago, some other LED-based applications in fiber have achieved secure key rates of 10.9 kilobits per second. And you can see the comparison with our system here. LED-based free space QKD can achieve 30 kilobits per second at 0.5 meters. We did ours at a distance of 10 meters. And other airborne demonstrations like satellite to ground, you can make the comparisons here as well. You can see that our system performs really well, and it's a system that can be improved upon farther.